He, and today I'll be presenting assignment 3 for INF2205 A credit card fraud detection MLOps pipeline built on Microsoft Azure. I will walk through the full projects from initial setup and design decision through pipeline execution and model comparison to deployment and critical reflection on the experience. I select the Microsoft Azure as my cloud platform. The key services I used were Azure Machine Learning Studio with Python SDK v2, Azure Block Storage for data management, Manage Online Endpoint for deployments, Azure DevOps for CI/CD, and Azure ML Spectra for automated hyperparameters learning. For the dataset, I used the Cargo credit card fraud detection dataset. It contains 284 and 807 transactions with only 0.17% being fraudulent. That's an instrument class imbalance of roughly 1 fraud for every 577 legitimate transactions. There are 30 features, 28 anonymized PCA components labeled V1 through V28, plus time and amount. This is a classic and challenge real-time datasets used in the financial industry. So let me walk through the 6 component key, that I built. First, I five-step ML pipeline: ingest, prepare with smoke, compare the 3 models, evaluate models, and deploy. Second, the Azure ML model registry, where I register the best model. Third, a manage online pipeline endpoint called fraud endpoint for real-time risk scoring. Fourth, a CI/CD pipeline using Azure DevOps. Fifth, an automated hyperparameters webjob across 6 S3 pools reconfiguration. And 6, endpoint monitoring through the Azure ML Studio GUI. Here's the complete end-to-end architecture, starting from the raw data in Azure Block Storage. The pipeline flows through 5 steps. Ingest loads and validates the raw CSV data, apply standard scalar normalization and smooth oversampling. Importantly, only on training set to prevent data linkage. Compare chain 3 models in parallel, attributes, random forest, and logistic regression, and automatically selects the best one by ROC, AUC. Evaluate compute final matches on the held-out test set. And finally, the best model is deployed to manage online endpoint. All of this is authenticated using the Python SDK v2 on an Azure Compute cluster. At the bottom, you can see the CI/CD loop, where the code is pushed to Azure repos. DevOps detect the change and automatically trigger a new training run. This is the core principle of MLOps, automated, reproducible retraining. And then let me explain the 4 key design decisions behind this pipeline. First, why 3 models? Comparing attributes and random forest as tree-based ensample method against logistic regression as a linear baseline give a complete picture of what type of models work for this problem. This is important for justifying the final model choice. Second, why small only on training set with only 0.17% fraud? A naive model would predict legitimacy for everything and achieve 99.8% accuracy while being completely useless. Small fix it, but it must only to be applied to training data. In my first pipeline version, I made the mistake of applying it to full dataset before setting, which caused the data linkage. I caught and fixed this in version 2. Third, why a 5-step pipeline? Separating concern means each step can be run independently. If I change the model, I don't need to ingest the data. The modularity is essential for production MLOps. Fourth, why SDK for the pipeline but GUI for monitoring? The SDK produces reproducible version control code that integrates with CI/CD. GUI is more intuitive for vision inspection of latency and throughput, which is where you want to see the trend at a glance. One of the key requirements of this assignment is to reflect when to use GUI, CLI, or SDK. Here's exactly how I apply it. I use the Azure CLI to create a workspace and resource good. It is the faster way to set up infrastructure and it is scriptable. I also use CLI for uploading the 150 MB CSV file to block storage because the portable GUI upload is unreliable for large files. I use the Python SDK for registering data assets, running the pipeline, configuring the web job, and deploying the endpoint. All activities that need to be reproducible and version controlled. I use the GUI for monitoring endpoint matches because visual latency charts are more intuitive than pasting JSON output. For CI/CD, I use combination the Azure DevOps usable interface to set up the pipeline plus YAML for the pipeline definition, so it's stored in version control alongside the code. The key insight is that there is no single best mechanism. The right choice depends on whether reproducibility matters, the file size, and the nature of the activity. For the components connection, the blob storage data is registered as a data asset in Azure ML referenced by a URI path. This is passed as an input to the ingest step. Each step output folder automatically becomes the next step input. This is how the pipeline chain together without any manual file management. Once the compare step finished, the best model by ROC/AUC is automatically selected and saved as model.pkl file. This gets registered in the model registry. The deploy script then fetches this registered model, packaging it with the scoring script, and serve it via the managed endpoint. Finally, the CI/CD loop closes when a code change is pushed to Azure Lab repos, when triggers the DevOps pipeline to run the pipeline py file and kick off a new running. Here you can see the actual pipeline execution in Azure ML Studio, or 4 processing steps: data ingestion, feature engineering, model comparison, and evaluate best model, completely successfully shown by the green check marks. The output at the bottom shows the trained model comparison result and matrix reason all produced accurately. This is the pipeline job which run as a part of correct version pipeline with the proper smooth handling. On the left, you can see the model registry showing the fraud detection attribute version 1 registered as a custom type model for the credit card fraud experiment. On the right, you can see the fraud endpoint detail page. You can see the provision state is a C, fraud v2 is receiving 100% of live traffic, and the scoring script is called py file. The endpoint was created on standard F2 SB2UM. I have to switch from the DS to V2 due to quota limitation on the student limitation subscription. And at the bottom, the live test result prediction 0, meaning legitimate transaction with a fraud probability of 8.31 times 10 to the minus 5. Here's the terminal showing the actual live code to the deploy endpoint running Python 3 test endpoint py file send a real HTTP request to fraud endpoint and receive back this JSON response. Prediction 0 means the transaction is legitimate. The fraud probability is 0.008%, correctly identified as a non-fraudulent. Response latency is approximately 4 to 6 milliseconds, which is production's grade speed for real-time fraud detections. Now for one of the most important critical reflection. When I first ran the pipeline, I got the perfect ROC/AUC of 1.0. This is actually a red flag, not a success. The problem was that I applied smooth to the entire dataset before splitting into training and test set. Smooth creates synthetic sample by interpolating between real minors class example when those synthetic samples appear in both training and test set. The model essentially memorized pattern that is sensible. This is called data lineage. The test set is no longer independent, so the evaluation matrices are artificially inflated. In version 2, I correct this. I now split the dataset first, then I apply smooth only to the training set. The test set contains only orange real transaction. The corrected ROC/AUC is 0.99965. Still excellent, but now more trustable. This is a very common mistake in practical, and catching it demonstrates exactly how careful pipeline design is very important in MLPS. Here are the results comparing all 3 models. Random forest win have the highest ROC/AUC. XGBoost come in second. Logistic regression significant the worst, and this can confirm 2 things. First, random forest is the best choice for the dataset. Second, and more importantly, the gap between logistic regression and the tree-based method prove that fraud patterns in this PCA transform feature space are highly nonlinear. A linear model simply cannot capture them very enough. This kind of evidence-based model selection is what distinguishes a proper MLPS pipeline from just training a single models. Here you can see the Azure ML Studio showing the fraud attributes web experiments with all 6 attributes web trial complete successfully. Each trial tests a different combination of n estimators, my step, and learning rate parameters, all running on the fraud cluster compute target.